Hello students, welcome back to Math 332 Linear Algebra. We are going to start a new chapter today, and in this video, which is on section 5.1, we are going to make an introduction of what is the eigenvectors and eigenvalue of a matrix, and we are going to talk about the concept of eigenspace and the concept of algebraic and geometric multiplicity for eigenvalue. All right, so without further ado, let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know how to compute the eigenvalue and eigenvectors for matrix A. And given a particular eigenvalue, lambda, you should know how to compute something that we call eigenspace, E lambda. And given an eigenvalue, lambda, you should know how to compute the algebraic and geometric multiplicity of lambda. So what is eigenvector and what is eigenvalue? Well, let me first tell you a story. When I was in middle school, my room is always a mess, and my mom is always not very happy about it. And she always, asked me to clean things up and all that kind of stuff. And I managed to convince her that all this efforts is going to be futile because the world is just going to get more and more messier instead of getting more and more order. And I didn't know about that concept. Actually, this is a concept of entropy. But I remember I gave her an example which is if you have a book, 100 pages, let's say you tear all of them out, arrange them from page 1 to page 100 in this order, page 1, 2, 3, 4, all the way to 100. And let's say you throw the entire book up and then let it shatter everywhere. And you will see that it's almost impossible to have your book rearranged according to the perfect order 1, 2, 3, 4, all the way to 100. Most probably that the pages will be like say page 25, page 100, page 29, page 12, and everything is going to be in this order. And the reason is very simple because in order to have the book to fall back to the original positions, that is only one way you can do it, which is page 1, page 2, page 3, all the way to page 100. But they are way more likely to be out of order. There's so many ways the arrangement can be out of order rather than can be in order. So same thing with the situation I'm trying to describe right here. So you have a matrix, let's say 2 by 2. Okay, you have a vectors, let's say 2 by 1. Now, if you multiply them, if you multiply these two vectors, you will get another vectors, W, which is 2 by 1. Now, your V is right here, okay? And there's only two different ways you can end up to be parallel to V. So either your W is like this is one way to be parallel to vector V, or another way to be parallel to vector V is this. Most of the time, more likely, after you multiply a vector V, more likely your W, okay, will be something that looks like this, or something that is look like this, or something that looks like this, or something that looks like this. The reason is there are infinitely many ways to be not parallels to V, but there are only two ways. You can kind of like get two different ways to get parallels to V, but most likely you will get something that is not parallels to V. So if you multiply a matrix A with V, and then you get a vector that's like this, 10V, if this is your new W. So you are going to be still in the direction of V, so you have like 10V, right? Or you have AV, and then you get like negative 5V. So this is a situation where you are still parallels to V, but you are pointing in the opposite directions. So when this happens, this is rare, and this is rare, and rare become precious. So this is a very special situation, and we give this vector a special name. This vector is going to be named, it's going to be called as an eigenvectors. And this number right here is going to be called eigenvalue, okay? All right, let's look at this particular example. So you have a matrix A, you have a vector U, and you have a vector V. So if you do this computation AU, and you will see that this is the W, right? The products W using the notations that we have previously. And you see that if you multiply negative 4 out, you will get this vector here. This vector here is exactly your U. So now you see that your AU is equal to negative 4U. So this is a very rare occasion, okay? So it's a very rare occasions. This vector now become very precious, and they have a special names. This vector U here is called the eigenvectors, and this number here is called the eigenvalue, all right? So if you take this vector V instead and multiply it with A, you will see that you get this W, And this is no way that you can write this as a product of an alpha together with these vectors. So in this case, you will see that your AV can never equals to some number, okay, and then V. So this is not a very precious. This is what is supposed to happen most likely, right? So this is not some things that we want. So this is not the eigenvectors or eigenvalue, okay? But this is an eigenvectors, and this is the eigenvalue. So let's look at the definitions, okay? So this is the definition right here. So if you have a square matrix, has to be square, all right? A scalar has to be scalar, which is a number. It's called an eigenvalue of a vectors of a matrix A if there is a non-zero vector x. This vector x here has to be non-zero. This is very critical because if your vector is 0, then the situation is very trivial. So we want to pick up a vectors that is not 0, because if you have 0, A multiplies 0 always give you 0. Right, so you can multiply whatever lambda here, so you'll be like, oh, eigenvector, eigenvector, eigenvalue. No. So if you have a 0 vectors, that doesn't count, okay? So we wanted our eigenvectors, this particular vector x here, to be non-zero. This is critical. You always have to remember that. So if you have a scalar, okay, that scalar lambda is called an eigenvalue. If you can find a vectors x which is non-zero such that ax is equal to lambda x. Okay, when you have ax equal to lambda x, where lambda is a number, that lambda can be 0 though. The lambda can be 0. That's a possibility. The only thing they don't want it to be 0 is the vector. So be careful, right? Non-zero vector x. But they never say about the lambda. Lambda can actually be equal to 0. All right, so make sure you know if you have a non-zero vector x, you multiply it with a and you get lambda x, okay? Then this lambda here is known as the eigenvalue, and this non-zero vector x here is known as an eigenvector, okay? All right, wonderful. Now, the question is, if you are given a square matrix A, how do you find this vector x, and how do you find this number lambda, okay? Now, so in order to find, okay, this vector x, all right, and this number lambda, what we're going to do is we look at this equations, ax equals to lambda x, okay? I am going to move lambda x to the other side, so I'm going to move that like this, and this is going to be a 0 vectors. Now I'm going to factor out my x. I can do that, but be careful. We can only do factorization like this, okay? X, right? And another things you know from before, you cannot write like this. This is nonsense because this is an n by n matrix, and this is a number. When you have an n by n matrix, you cannot subtract it with a number. All right, matrices you can only add and subtract them if they are of the same size. So factorizations will require you to use an identity matrix right here. So this is an identity matrix, okay? This is n by n identity matrix. So now we have this is still n by n, okay? So we have that equals to 0. Now what? Okay, so recall that this x here, this vector x here, this vector x here has to be non-zero. So if you want to have these equations, okay, to produce a non-zero vector x as a solutions, then you better make sure that this matrix here is non-invertible. Let me say that again. If you want this x to be non-zero, so you want the x to be non-zero, okay? Because obviously one of the solutions here is the 0 vectors. So if you have x equal to 0, this is good, right? But if you want to have a non-zero solutions, if you want to have x here to be a non-zero solutions, then you better make sure this matrix is not invertible. Because if this matrix is invertible, just like the homework problems that you have seen a long time ago, if this matrix here is invertible, the only solution for the x right here is 0, right? So if bx equal to 0, okay, if b is invertible, then your x is the product of these two matrices, and that will be obviously 0. So we want to make sure that we do not want this particular matrix here. We do not want this particular matrix here to be invertible. So how do you do that? Well, if you set the determinant of a minus lambda I, if you set it equal to 0, all right, then this matrix a minus lambda I will not be invertible. This is not invertible. This is definitely not invertible now. Then you will get x, okay? Then you will get x that is not equal to 0. All right, so in order to find the eigenvector and eigenvalue, what we first do is to make sure this matrix here is not invertible. that is to make sure that this determinant here is equal to 0. By doing that, we will be able to find the lambda. Okay, so once we have the lambda, we will be able to find the vector x. Okay, so there's a theorem right here which basically summarizes what we just discussed. That is like A is an n by n square matrix, and lambda is an eigenvalue of this matrix A if and only if this determinant here has to be equal to 0. Okay, all right, so this lambda here is an eigenvalue of a matrix A, then this determinant here will be 0, so that the matrix is not invertible, so that you will have a solution that is not equal to 0, and that solution that's not equal to 0, okay, is going to be our eigenvector. Okay, and this particular properties here, this particular determinant here has a name, because once you compute this determinant, you will see in a minute that you will get a bunch of equations. You get a polynomial actually in lambda, and that equations that corresponding to this determinant is called the characteristic equation of this matrix A. All right, so this is called the characteristic equation of this matrix A. So in order to compute the eigenvector and eigenvalue, the first thing you do is to compute this determinant, solve for the lambda, and then put the lambda back into this equation, and then solve for x. Okay, so the eigenvector and eigenvalue problems, to solve them, you actually always find the eigenvalue first. Okay, all right, so let's look at how we actually do that. All right, so now we have a matrix A. All right, the question is find all the eigenvalues, and after that, find all the eigenvectors corresponding to those eigenvalues. Okay, so what we do is we compute this determinant. So it takes the matrix A minus lambda I. Okay, so what do we have? So we have this, right? A, okay, minus lambda I, which looks like this. So you have a matrix that looks like that. Take the determinant and set it equal to 0. So computing the determinant and set it equal to 0, what do you have? Well, you will get something that looks like this. All right, computing this determinant, meaning that you have to take this entries, multiply this, and then minus 6 times 5, which is 30. So you get something that looks like that. Expand everything out, regroup, and it turns out you have a quadratic equation, lambda squared minus 3 lambda minus 28. Obviously, you can factor it like that. And now you see that lambda equals to negative 4 is one of the eigenvalue, and lambda equal to 7 is another eigenvalue. Okay, so once we have these two so-called eigenvalue, for each of the eigenvalue, we should be able to find the corresponding eigenvector. So for this eigenvalue, we should be able to find an x. Okay, right? That's an eigenvector corresponding to this particular eigenvalue. We want to find something that's ax equals to negative 4x. Okay, and then for this one here, we'll find another eigenvalue. So let's say that one is called v. So we want to find v. So that will be like av equals to 7v. So for every eigenvalue, that will correspond to, you can find a corresponding eigenvectors. So you can find one eigenvector here. You can find one eigenvector here, for example. Okay, so let's do that. All right, so let's back to these equations, right? Ax equals to lambda x. All right, so if you are looking for the eigenvectors corresponding to lambda equals negative 4, so you will be solving a minus lambda I, okay, x equals to 0. But then your lambda here is going to be negative 4, so you will be solving this system, negative 4i, right, okay, x equals to 0. So that means you are going to take your a and then plus 4i, right, and then solve the system of equations. So that is the same as looking at this particular augmented matrix. This is the augmented matrix correspond to this. And once you substitute the lambda, which is our negative 4, you will get to this. This one right here, 5, 6, 5, 6, is exactly this particular matrix here. Because our matrix A, what is our matrix A? So our matrix A here is 1, 6, 5, 2. So you add 4, 0, 0, 4. You will get 5, 6, 5, 6. This is exactly the matrix, the augmented matrix that correspond to the systems. So let's solve for x. We know how to do that. That's basically just solve for a system of linear equations. We know how to do this. So actually, this is very simple. You see that the entire second row is just repeating the first row. So if you do the row reduction, immediately you will get to here. So we know that this could be taken as a pivot. and this will be taken as a free variable. So your y here will be a free variable, and you can write x equals to -5 or -6/5y. So you can write as this. And we have a bunch of eigenvectors. We have a whole bunch of it because all the x and y, if you can write it like this will actually give you a, okay, vector x equals to -4 vector x. So we just want to pick one vector that is convenient for us. So as you can see, there are infinitely many solutions here. And this is actually not a surprise because we want the matrix to be non-invertible. So we want this matrix to be non-invertible. So we actually do have infinitely many solutions, but we only pick one, right? We're going to pick one eigenvectors. All right, we're going to pick one eigenvectors, and no one really likes fractions. So in order to get rid of fraction, I can choose my y here to be -5, for example, to be -5, okay? And then this will be one of the solutions. This is definitely one of the solutions for the system. So therefore, I have something that looks like this. All right, I have something that looks like this. With that, I will say that -4 is an eigenvalue corresponding to this particular eigenvectors 6, -5. Okay? All right, now that you know how to compute the eigenvalues and eigenvectors, I want to introduce you to another concept. That's concept of eigenspace corresponding to eigenvalue lambda. So what is an eigenspace? So you compute the eigenvalue problem, which is this. You found lambda, okay, and from this lambda, you get a whole bunch of eigenvectors. This is what we have seen from the previous example. And now you construct a set, okay? You construct a set, and you put a 0 into that set, and then you put all your eigenvectors into this set, right? So all the eigenvectors corresponds to this eigenvalue lambda. You put it in this set. So you have some x, some w, some v, whatever. So you put all the eigenvectors into this set. This set's right here, okay, together with the 0 vectors. Your 0 vectors is not supposed to be the solutions of the system. So your 0 vectors is not supposed to be one of the eigenvectors. So you add the 0 vectors into that set and then put all the actual non-zero eigenvectors into this set. This set now is known as the eigenspace of lambda. Okay, so notation here is E lambda. Okay, so let's look at the example. So right here, you see that lambda equals to -4. This is what we have from before. So I want to construct the eigenspace, okay, corresponds to lambda equals to -4. Sometimes I write like this, but sometimes I just simply write like this. So this is a set of stuff, right? So first thing you have to do is to put a 0 vector into that set, and then collect all the vectors that is all the eigenvectors corresponding to lambda equals to -4, and we know that they are all like this. They are like -5, -6 and -5, right? They are 6 and -5, and any multiple of it, right? So the multiple here, this y here actually cannot be 0 because this is an eigenvector. So eigenvector cannot be 0, but so this y here is not supposed to be 0. But when y equal to 0, I have that already, so that's fine. So it's basically a collection of vectors that looks like this and looks like this. And actually, as you can see, this one right here is actually the span of 6, -5. Right? So now you can actually also see that this eigenspace corresponding to lambda equals to -4 is, by definitions, a set that consists of 0 vectors and all the eigenvectors, right? All the eigenvectors for the eigenvalue lambda equal to -4, and it turns out that it is actually the span of 6 and -5, right? So this particular span, 6, -5 here, is the eigenspace for lambda equals to -4, okay? Let's do the same thing here for lambda equal to 7. So for lambda equal to 7, what is the eigenspace? Okay, so what is the eigenspace for lambda equal to 7? So sometimes I write like this, sometimes I write like this. So by definitions, this is a collection of set which consists of the 0 vectors and all the eigenvectors corresponding to the eigenvalue lambda equals to 7. So they all looks like this. Right, again, this y here cannot be 0, okay? Because if the y here equal to 0, you have 0 vectors. 0 vectors is not an eigenvectors. So all these are supposed to be eigenvectors, okay? So these are non-zero. Okay, these are non-zero vectors. So we are looking for all the vectors that is like this. If your y is not equal to 0, these are all the eigenvectors. These are never eigenvectors. This is not an eigenvectors. Okay, remember from the definition of eigenvectors, your eigenvectors can never be 0. So this is not an eigenvectors. But for eigenspace, we put this 0 vector into the set. That's the part of the requirement. Okay, that's the requirement. That's the definition. All right, so it will consist, the eigenspace will consist of the 0 vectors and everything that looks like this, which is actually, this is going to be, so this set here is actually nothing but the span of 1, 1. Because the span of 1, 1 will contain all the things that looks like that, all the vectors that looks like that, and also it will contain the 0 vectors. So E7 is span of 1, 1, and E negative 4 is span of 6 and negative 5. Okay. Right, let's summarize what we have so far. So we see that our eigenspace of lambda equals to negative 4 is spans of 6 and negative 5. Our eigenspace of lambda equal to 7 is span of 1, 1. Now, E negative 4 is a vector space because span of any vectors is a vector space. This is actually a subspace. This is actually a subspace of R2. All right, isn't it? And E7 is the span of the vector 1, 1. Again, the span of any vectors is a vector space. So this is actually a vector space. And this is also actually a subspace of R2. So these are actually vector spaces. That's the reason why we call them eigenspace, right? They are actually vector spaces. And for every vector space, we can look at the dimensions. So for example, in this case, obviously, this one here, the dimensions of E negative 4 is 1, right? Okay, this is actually the basis, right? So here the dimensions of E7 is also 1, right? Because once we have a vector space, we can look at the dimension. The dimension of the vector space is defined as the number of bases, number of vectors in the basis, number of vectors in the basis. So here we can select 6, 5 as a basis, okay, as a basis for E negative 4. And E7s, we can select 1, 1 as a basis. So they have one vector in the basis. So that gives us the dimensions. Now, look at this definition here, right? So if you have an eigenvalue, let's call it lambda naught of a matrix, okay? The dimensions of the eigenspace, the dimension of the eigenspace is called geometric multiplicity of that eigenvalue. So right here, we can see that the dimension here is 1, so the geometric multiplicity for lambda equals to negative 4 is 1. Same thing here, the geometric multiplicity of lambda equals to 7 is also 1. So geometric multiplicity is the dimensions of the eigenspace. Geometric multiplicity is the dimensions of the eigenspace. Algebraic multiplicity for the eigenvalue is the number of times, okay, these terms appear in the characteristic equation. So how many times these terms here, how many times lambda minus, okay, minus 4 appear in the characteristic polynomial, right? In the characteristic polynomial or characteristic equations. Well, if you remember, if you expand all this characteristic polynomial out, you will remember that we have an equation that looks like this, right? So lambda equals to negative 4 appear as one time, right? Appear as one factor. This is only one factor in the characteristic equations. So lambda equals to negative 4 has algebraic multiplicity 1 because of this. Okay, lambda equal to 7 also have algebraic multiplicity 1s because this factor appear only one time in the characteristic equations. So algebraic multiplicity will count the number of factor in the characteristic equations, the number of factor that looks like this in the characteristic equations. And the geometric multiplicity is not going to look at the number of factors, but it will looking at the dimensions of the eigenspace. So the dimension of the eigenspace. Okay, so dimension 1, so geometric multiplicity 1 appear one time here. That's algebraic multiplicity 1. So as a summary, the eigenspace, the eigenvalue lambda equals to negative 4 has algebraic and also geometric multiplicity 1. And so is the eigenvalue lambda equal to 7. Lambda equal to 7 also have algebraic and geometric multiplicity 1. Okay. Now, I want you to take a look at this question. So things are slightly more complicated now because we have a 3x3 matrix. So go through all the process that we discussed before. Find the characteristic equation. That's always the first steps. Use the characteristic equation to find the eigenvalue. Find a basis for the eigenspace. You need basis for the eigenspace so that you can talk about the geometric multiplicity. So algebraic multiplicity, you can find that information in the characteristic equations, but geometric multiplicity, you will have to look at the eigenspace. All right, so let's do all of that, and we'll come back and talk about the solutions. All right, let's take a moment to think about the problem, and you should pause the video. And when you think you have the solutions, you can restart the video and we will look at the solution together, okay? All right, welcome back. So to find the characteristic equation of A, we'll have to compute this determinant. We'll have to compute the determinant of A minus lambda I, set it equal to 0, and solve for the lambda. Solve for the lambda. So you get into this characteristic equations, sometimes also called characteristic polynomial. You can factor them. So immediately you see that this is lambda plus 1 square with a negative right in front of it, and then lambda minus 2 equals to 0. This is power 1, this is power 2. So immediately we know that lambda equals to negative 1 will have algebraic multiplicity 2 because this factor appears twice in the characteristic equations, and lambda equal to 2 has algebraic multiplicity 1 because this factor appears one time in the characteristic equations. All right, so now how do we find the information here regarding the eigenvalues? Eigenvalues, we have that already. Characteristic equation, we have that already. So we need to look at the eigenspace now. So what is the eigenspace? So the eigenspace corresponds to lambda equals to negative 1. So the eigenspace corresponds to lambda equal to negative 1. By definition, it's a set that contain the 0 vectors. You have to add this thing in artificially. And then it also contains all the eigenvectors, right? All the eigenvectors corresponds to lambda equals to negative 1. And we know from our computation here, we know that all the eigenvectors actually span, actually can be written as a linear combinations of these two vectors right here, right? So here our y and z are not supposed to be 0. But that case is actually covered by this right here. So actually, if you look at it carefully, it is actually nothing but the span of this two vector right here, negative 1, 1, 0, and negative 1, 0, 1. So actually, the eigenspace, okay, of lambda equals to negative 1 is the span of these two vectors. So if you are looking for the basis for this eigenspace, so the basis can be taken as a set consists of these two vectors. Okay, so the basis can be taken as a set consists of these two vectors, which give us the dimensions of the eigenspace. So what's the dimension of the eigenspace? The dimension of the eigenspace is 2. So what's the geometric multiplicity for this eigenspace? So the geometric multiplicity for this eigenvalue lambda equals to negative 1 is 2, because the geometric multiplicity for a particular eigenvalue lambda, is the dimensions of the eigenspace. So the dimension of the eigenspace is 2. So this is what happened right here. E, negative 1 is spanned by these two vectors. So the eigenspace for this is dimension 2. Okay, so geometric multiplicity for lambda equals to negative 1 is also 2. So lambda equal to 1 has algebraic multiplicity 2 and also geometric multiplicity 2. How about the other eigenvalue? So the other eigenvalue is lambda equal to 2. Right, go for it. Okay, the eigenspace of this lambda equal to 2 by definitions is a set consists of the 0 vectors and also the actual eigenvectors. So all the eigenvectors is going to be like this. Z here is not supposed to be 0 because eigenvectors can never be 0. But then we artificially put a 0 into that set. So this is actually the span. So E2 is actually the span of this vector 1, 1, 1. So Z2 is actually the span of this vector 1, 1, 1. And so the vector 1, 1, 1 can be used as a basis, okay, as a basis for the eigenspace. So you can clearly see that E2 is dimension 1. So E2 is dimension 1, so the geometric multiplicity for this eigenvalue here is actually 1. And also the algebraic multiplicity is also 1 because we have seen this now, this thing here appear like that in the characteristic equations. So this eigenvalue lambda equal to 2 has algebraic multiplicity 1 and the geometric multiplicity is also 1. All right. So now we're going to move to the next questions right here. Almost the same type of questions, exactly the same type of questions, but now we have this 4x4 matrix. The characteristic polynomial, all that is pretty easy to compute actually, even though it's 4x4. You will see in a minute why I said that. And I want you to take a look at these problems, and we'll see the solution later. Okay. All right, let's take a moment to think about these problems, and you can pause the video, and when you think you already have the answers, you can restart the video, and we can look at the solutions together. Okay. All right, let's look at the solutions. So in order to find the characteristic equations, we have to compute the following determinant. And this determinant is easy to compute because your matrix is upper triangular. So you are basically compute a determinant that kind of looks like this, right? These are all 0. I don't even care what happened here. This is nothing but the product. This is nothing but the product. Okay, this is nothing but the product of the entries into diagonal. So you have that. So if you set it equal to 0, I can take out the negative, so I can rearrange it so that I will have this. So I will have this equal to 0. So immediately from here, you will see this lambda equal to 2 have algebraic multiplicity 3. Okay, so algebraic multiplicity 3. And also from here, you will see lambda equals 4 have algebraic multiplicity 1. All right, so we have algebraic multiplicity 1. That's easy, that's straightforward. And in order to compute the geometric multiplicity, we'll have to look at the eigenspace. So the eigenspace corresponding to this eigenvalue lambda equal to 2 is by definition a set consists of the 0 vectors and all the eigenvectors corresponding to lambda equals to 2. So this eigenvectors corresponds to lambda equal to 2 if you do the computation. Turns out that they are all going to be multiple of these vectors. Okay, they're all going to be a multiple of these vectors. Okay, they are all multiple of these vectors. Let's say, I don't know, let's call it y or something. All multiple of it. Let's say alpha. Okay, let's say alpha. Alpha is not equal to 0. They are all going to be multiple of the vector 1, 0, 0, and alpha not equal to 0. But if you look at this, okay, you can see that actually it is the span. Okay, E2 is actually the span of this vector 1, 0, 0, 0, which means E2 right here is of dimension 1. So E2 right here is of dimension 1. So lambda equal to 2 have algebraic multiplicity 3, but the geometric multiplicity is only 1. So the geometric multiplicity is the dimension of the eigenspace, and you will see that it is actually only 1. This is going to give us trouble. You will see that in the next video. This is actually going to give us some problem. But right now, we don't really care. We just look at the definitions. And from the definitions, geometric multiplicity is 1 for the case lambda equal to 2, for the eigenvalue lambda equal to 2. If you do lambda equal to 4, okay, so if you actually compute that, okay, so and you will be able to row reduce, and you'll be able to find the eigenvectors corresponding to eigenvalue lambda equal to 4. So we can construct this eigenspace right here. So the eigenspace right here, by definition, is a set consists of the vector 0 and all the eigenvectors. So all the eigenvectors is actually of the form of 1, 2, 4, 4, a multiple of it. Okay, here, this here cannot be 0, but it's going to be like that. Okay, your eigenspace right now will be the 0 vectors and all the eigenvectors. Eigenvectors for this eigenvalue lambda equal to 4 will be a multiple of 1, 2, 4, 4. And this multiple here cannot be 0. I think you know, because eigenvectors are not supposed to be 0. So this alpha here is actually a non-zero number. But together with the 0 vectors that we artificially insert into that set, your E4 is actually the span of 1, 2, 4, 4, which means your E4 is of dimension 1, which means the geometric multiplicity is 1 for this lambda equal to 4. The algebraic multiplicity is also 1 because if you recall, if you go back to the computation right here, you see that the algebraic multiplicity is 1 and the geometric multiplicity in this case is actually also 1. Now, you don't really know why are we computing this. You will see it how we need it in the future, but right now, you don't really need to know why we need that. We'll see that in the future, but the key thing is you need to know how to compute the algebraic multiplicity for eigenvalue. That is the number of times this factor, let's say I write like this factor, how many times this factor appear in the characteristic equation. And for geometric multiplicity, you will have to actually compute the eigenspace. And the key thing about eigenspace is, look at the definition. So the eigenspace is the set consists of the zero vectors and the eigenvectors. Okay, the eigenvectors, all the eigenvectors corresponding to lambda equals to lambda naught. So these are non-zero vectors. Okay, these are non-zero vectors. Be careful. Eigenvectors are never zero by definitions. Eigenvectors is never zero by definitions, but together with a zero here, you can most certainly see that your solution will be in the form of span of something. So from here, you'll be able to tell the dimensions of the eigenspace, and from here, you'll be able to tell the geometric multiplicity. So geometric multiplicity require a little bit more work. Algebraic multiplicity is just looking at the number of times that factor appear in the characteristic equations. All right. All right, this concludes our discussion for this section. And in the next video, we are going to look at the concept of diagonalizations. And in that video, you will be able to see how the eigenvectors and eigenvalue play a very important role in order to help diagonalize a matrix. And you might wonder, why do we need to diagonalize a matrix? Well, we're going to show you in this course two applications of diagonalizations. One of them is using the process of diagonalizations to solve a system of differential equations. And another one is an application of how to use diagonalization process to solve something that we call a difference equations. All right, we'll get there eventually, and I will see you very soon.